All right, we're now looking at day 3 of our 1.2 notes. This is our last day of 1.2. It's a big section. So we're going to do identifying if a function is even or odd. Identify vertical and horizontal asymptotes. That's a review from last year. And determining the end behavior. That's also a review from last year. So the only new thing is identifying if a function is even or odd. Okay, so even functions. How do we know a function is even? There's 3 ways. We can do it graphically, and if it's even, then it's symmetrical about the y-axis. So it's like a little flipped over thing, and we'll look at some examples of that. Numerically, you can tell it if it's by numerically that if xy is a point, then negative xy is also a point. And again, we'll look at that when we look at our graphs. And then we have algebraically. And for algebraically, we see if f of negative x is actually equal to f of x. And if that's true, then it is an even function. Odd functions, similarly, we have odd functions the same way. We can tell graphically. However, they're symmetrical about the origin. And we'll kind of see what that means when we have our pictures. In example 1, we can see if they're numerically. This is slightly different, right? If xy is a point, then negative x, negative y. So here it was just negative x, positive y, and here it's negative x, negative y is a point. And then we can see it algebraically. And algebraically is different because f of x is going to be equal to negative f of x. Okay? Functions can also be neither. Okay, so they might be none of these things, and that's okay too. So, looking at example 1, we have 3 graphs here. This first one is an even function. Okay, and you can kind of see how it like folds over, like this side and this side are exact copies of each other. Okay, and that numerical thing, since this is a point, right, if this is x, y, then we can see that this is also a point, right, and it's the same y value, it's just the opposite side, right, so it's the opposite x, y. The next one is an odd function. Okay. And so an odd function, what that symmetry around the origin means is if you start at like 0 and you take this piece and like you flip it over, then it's equal to that piece. So you can kind of see how those 2 pieces are the same. One's just like flipped to the other side. It's like flipped twice. Okay? And same idea, right? This, if this is just any point x, y, then here, right, I'm now on the opposite side of both. Right? So I have the opposite x and the opposite y, and that point is still on my graph. Okay? If we look at our next one, right, you can kind of see how this one, it's not really at the origin. Like if I start here at this point, it doesn't really flip it correctly. Okay, I'd have to like jump down here in order to be like the same as up here, and that doesn't make sense. So this is a function that's neither. So it does have symmetry, but it's like 2 lines of symmetry would be like the y-axis, and then like be up here. And that's not the origin. Okay, so that's kind of the difference with that neither. Or if you can just say like they're not any way symmetrical at all, then it's also neither. Okay. So what we're going to do is we're going to look at some examples, and we're going to determine whether the function is even, odd, or neither algebraically first, and then we'll just check graphically so we can see a few more examples of that. Okay. So the first thing we always check for is even. I'm going to write even. Question mark. Okay. And in order to check it's even, right, we put an f of negative x. Okay, because we want f of negative x to equal f of x. We'll jump around. Okay. So what we do with f of negative x is anywhere there's an x, I'm going to put in that negative. So there's an x here, so instead of x, I put parentheses, and I put negative x to the fourth. Plus, again, there's parentheses, or there's an x, so I put negative x squared. So now I need to know what negative x to the fourth is. Well, negative x to the fourth is negative x times right? And negative x times negative x is positive x squared. A positive times a negative is then negative x cubed. A negative times a negative is then a positive. So this whole thing is going to equal x is the same as x to the fourth, right? Because I had an even number of negatives being multiplied, it gives me a positive number. So this is just 2, and that negative x to the fourth is the same as x to the fourth. I'm going to do the same thing with negative x squared. Right? Again, a negative times a negative is positive. So that's the same as and then just plus 1. Okay, this piece here is the same as f of x. So I can say f of negative x equals f of x. This function is even. So now we're going to check graphically, and to check graphically, again, we're just going to open Desmos. Do I have Desmos open? I do. Oh, it's not showing me the other part. So we had 2x to the fourth, plus x squared plus 1. So again, we can kind of see how these two pieces here are symmetrical. Okay, if I put in that line, right, the two pieces on either side of that line are exactly equal. Let's look at another example, example B. So we have g of x equals 2x cubed plus x plus 1. So again, I'm going to check if it's even first. So I'm going to take my function, g of the opposite of x. I'm going to do 2, and it's the opposite of x cubed. Oops, let's make that black. Plus, and there's an x here, so I'm going to put the opposite of x plus 1. So just like we did before, the opposite of x cubed is negative x. I'm only going to have it 3 times. Well, a negative times a negative is positive, times a negative is negative. So this is negative x cubed. So that's 2 times negative x cubed plus negative x, that's just going to be minus x plus 1. Well, then I'm just going to simplify this. 2 times negative x cubed is negative 2x cubed minus x plus 1. So then I have to see, is this the same as my original function? And it's not. So g of negative x does not equal g of x. Okay? So this is not even. So now I want to check, is it odd? So I'm going to take this, and I'm just going to start right there. So right now we have g of negative x, equals negative 2x cubed minus x plus 1. Okay? To check if it's odd, if we look back up here, right, we have that f of negative x equals a negative f of x. So basically, I'm going to take a negative out of all of these terms by dividing by negative 1. So that negative from the negative 1 goes on the outside. A negative 2 divided by negative 1 is 2x cubed. Negative x divided by negative 1 is plus x. And 1 divided by negative 1 is minus 1. Okay. Now I want to check, is this the same as my original function? And if I look, right, I have 2x cubed, that looks good. X, that looks good. And this one I have plus 1, and this one I have minus 1. So no. So I can say g of negative x does not equal the opposite of g of x. So this function would be neither. It is neither even nor is it odd. And again, we can check that. With, it was 2x to the third plus x plus 1. Right, and this one's a little, right, it's not just flipping over this line. And if I put a line, also at y equals 0, right, we can see that like the pieces don't match up. So like this coordinate should be the same as this, and this coordinate should be the same as that. And they are not. All right, one last example of this kind. So we have h of x equals 2x cubed plus x. So we're going to check if it's even first. So I'm going to do h of negative x equals 2. And then I'm going to put in negative x cubed plus negative x. So as we saw before, negative x cubed is really 2 times negative x cubed, and then just minus that x then, right? And this is the same as negative 2x cubed minus x. Not h of x, right? So I can say h of negative x does not equal h of x. Now I want to check, is it odd? Well, again, I take this part here. So right now I have h of negative x equals negative 2x cubed minus x. I divide everything by negative 1. That negative 1 pops out. So I have negative 2 divided by negative 1 is just 2x cubed. Negative 1 divided by a negative is positive x. And if we look here, this piece here is the same as our original h of x. So I can say h of negative x is the same as that negative, and then that's not what I wanted to write. Negative h of x. So this function is odd. All right, our next piece is as I scroll down, asymptotes and end behavior. So what is an asymptote? So we have our asymptote here, and an asymptote is an imaginary line that a function approaches but never touches, right? And we have two types. We have our horizontal asymptotes, which go horizontally, and we have our vertical asymptotes, which go vertically. And those we learned about last year, right? And these graphs get closer and closer and closer, but they never quite touch as they do that. And end behavior is what number the graph is approaching on the far left and the far right. And we have our notation, right? The limit as x approaches infinity of f of x equals whatever. Or the limit as x approaches negative infinity of f of x equals whatever. All right, so let's look at some examples with this. For each function, we're going to identify the asymptotes, if there are any, and describe the end behavior. And we're going to do this by graphing. So I am actually going to split my screen, half this, half Desmos. So our first function is 2x to the fourth plus x squared plus 1. So I'm going to sketch that out. That one's still at me. The arrow goes below that x-axis, so we'll put that there. And it looks like it's just here and it goes way up. Okay. So, vertical asymptote, or let's start with horizontal. I'm going to be just going to abbreviate horizontal asymptote. There is none, right? As I go far to the left and far to the right, it's not like approaching a horizontal line. Okay, it'll be very obvious when they do. Okay? Polynomials don't have them. Okay, so it's when we have like, we're dividing by things or things like that, that we have those asymptotes. So a function like this would never really have anything like that. Same thing with our vertical asymptote. This has none. And behavior, it does have. So I want to know what's happening on the left as my graph goes to the far left and my graph goes to the far right. Okay. Let's do negative first. Okay, so negative infinity is the far left side of your graph. And as I keep going left, I can see this graph is going to go up and up and up and up forever. So as my graph goes to the left, my function is going up forever. Okay? So you can think of it like with this arrow. Because of that arrow, it's going up forever. The limit as x approaches infinity what's happening on the right? Well, as I go to the right, again, same thing, it's just going up and up and up forever. So again, since it's going up, up is our positive infinity. Okay, so that's what's happening on the left and what's happening on the right. Okay, B. We have 2x cubed plus x plus 1. An easy thing with Desmos is if you're like in a weird spot, just hit home. Those boxes are pretty even. Okay. So let's make a quick sketch of this. And these are not vertical asymptotes. Vertical asymptotes will have part of your function on both sides of it. This is going, it looks like it's going straight up, but it's not quite. It is going to keep moving to the right forever. Okay, so you'll see a vertical asymptote by things having like pieces of the graph on both sides. Okay, so this one, same thing. It has no horizontal asymptote. And it has no vertical asymptote. Again, these are just like a polynomial, right? Those vertical asymptotes and horizontal asymptotes comes from things we can't do. And remember, we can't divide by 0, and there's no division happening here. So it makes sense that nothing weird is happening. Okay? So let's look at our end behavior. The limit as x approaches, and keep doing that. I want to do negative first. It doesn't really matter which one you do first. Of f of x equals, again, what's happening on the far left? Well, where's our arrow going on the left? Our arrow's going down, right? So it's going down towards negative infinity. Same thing on the right. Where is our arrow going on the right? Well, it's going up towards positive infinity. Okay, so just be careful with like your positives and your negatives, and you have that notation down. Okay. Another example. We have h of x equals x cubed over x squared plus 2. So this is kind of weird in that middle part there, but it's just a slightly weird function. So again, we're used to our rational functions having weird things, and this is just like an example of a weird rational function that doesn't really have weird things happening with it. Kind of goes like that. Right, so it kind of goes like that. So while it is a rational function and I am dividing, if you try to solve x squared plus 2, right, it looks like our difference of squares almost, except it's not a difference, it's a plus. So this is something that while x squared plus 2 we are dividing, it can never equal 0, so it doesn't give us any weird situation. So we still have no horizontal asymptote. No vertical asymptote. We'll do our end behavior. We have the limit as x approaches negative infinity of f of x. All right, again, what's happening? X going towards negative infinity is the left side of our graph. So my arrow on the left is going this way, and it is going left, but it's also going down. Same thing with our other side, the limit as x approaches infinity. What's happening on our right? Well, with this arrow, it's going up forever. Okay. All right, looking at example D, I'm going to skip example D. It's going to be I think it's just going to, oh wait, no, this one, just kidding. I'm not going to skip it. It's a good one. So this is what this function looks like. So you have this like weird thing where it's like doing this, it dips down, and then it comes back up. And then that dip is right at 0, 0. Okay, so first, horizontal asymptotes. This one has one, right? As you see, it's getting closer and closer to like 1, but it's never actually touching it, right? If I like zoom in, it's never actually gonna hit. Like I can keep zooming and it's not actually there, right? And I could keep going, but it's never actually touching the number 1. Okay? So there's this line here. So my y value is never actually going to touch the number 1. For a vertical asymptote, there is no vertical asymptote. So that's still none. Then our end behavior, got a end behavior. The limit as x approaches negative infinity of f of x equals, well again, what am I going towards? What is this arrow going towards on my left side? Usually the ones we've seen so far, it's been going up forever or down forever. Well, this one, it can't go up forever. It's hitting the ceiling of 1. So that's where it's going towards. It's going towards 1. It's never going to reach it, but it's going towards it. Okay. Same thing on the other side. Where is this arrow going towards? Oh, it's going towards, same idea, right? 1. It's getting closer and closer to that line, even though it's never going to touch it. Okay, another example. We have x squared, sorry, I forgot the p of x. P of x equals x squared over x squared minus 4. Just going to change this function really quick. We have x squared minus 4. This is a nice one. So we have these different chunks. A lot of times with this, I find it almost easier to figure out my asymptotes first. So let's look for our horizontal asymptote. Do we have one? It looks like we do, right? Oops. But right, as I go along here, what's it getting closer and closer and closer to? Well, it's getting closer, I can even see with like the numbers, closer and closer and closer to the number 1. So there's a horizontal asymptote at y equals 1. Right, and what something nice that Desmos does, again, is if you just like click, it shows you what that point is, and as you drag it along, as you go, keep going, you can see that y value is getting smaller and smaller and closer to 1. But again, it's never actually going to get there. So here's our horizontal asymptote at y equals 1. My vertical asymptotes, if I click that home button again, what are these values getting closer? And so now vertical asymptotes have to do with your x, right? And if you watch our x value, it looks like it's getting really close to like -2. These two pieces are sandwiching it between x equals -2. And same thing on this side, right? It's getting closer and it's getting bigger and bigger and bigger. And it's probably going to get to +2. Okay, and you can zoom in, zoom out, kind of play around with it. But we have x equals -2 and x equals +2. So we're going to put that here. So that's -2. This is +2. And I'll draw it. Okay, so then the last thing we have to do for this is our end behavior. What's happening on the left? As I go to the left, right, again, I'm getting closer and closer to that line, which is at 1. What's happening on the right? Well, same idea. It's getting closer and closer and closer to that line, which is at 1. Okay. All right, last example. Q of x equals 3x over x squared plus 8x plus 12. So I'm actually going to zoom this one out because it is a weird situation. Actually, I'm just going to make it bigger. Okay. So we can find our horizontal asymptote first. And the weird thing about this one, which happens sometimes, is it kind of jumps over it and then gets closer to it. As I drag this along over here, you can see it's getting closer and closer and closer to 0, even though it jumped over 0 here. And that does happen sometimes. Okay? And this side too is getting closer. That y value is getting smaller and smaller and smaller, but it is getting closer to 0. So in the middle of your graph, sometimes your graph will jump over the asymptote and then like come at it from the other side, and that's okay. It's just a weird thing that happens. Okay. So our asymptote here is actually, there's 4 spaces for our graph. Oops. Is at y equals 0. Looking for our vertical asymptotes really quick, it looks to be about here, which is -6, and here, which is -2. Again, you can investigate that a little more with your graph as well. Or, if you're getting really good at your factoring, right, if you just look at your denominator, you can see that, yes, -6 and -2 makes sense. For what those are going to be. So let's draw it. So we have x equals -6 and x equals -2. And we have our horizontal at y equals 0. So this is like chilling up here. This is chilling over here. And this one's being weird and going up and then back down. That's kind of what it looks like there. Okay. So last thing, our end behavior. What's happening on the left? Sorry, left should be negative. Well, over here, again, I'm getting closer and closer to that horizontal asymptote. So that's 0. What's happening on the right? Again, same thing. It's getting closer and closer to that horizontal asymptote. Okay, so one thing you should notice, kind of like a takeaway here, is when you do not have a horizontal asymptote, your end behaviors are always going to like in these infinities, either positive or negative. When you do have a horizontal asymptote, right, your end behavior goes towards that horizontal asymptote. Okay, so that's a good thing to keep in mind. So yeah, again, those horizontal asymptotes and end behavior are very much connected. Right? That's it. See you guys.